Hello everybody. A little bit of another title for the video compared to my last ones, but let me tell you why I'm so excited for this video. So first of all, this is going to be the kind of like an introductory video to like a little mini series where I talk about different types of linkers and I talk about what makes them efficient, what makes them inefficient, what the research is into these linkers, things like that. So obviously, to preface that, we first have to talk about a little bit of an overview. We need to talk about the terminology we're going to use. We need to talk about the characteristics scientists are looking at. We need to talk about what linkers we're actually going to be looking at in this mini-series, which is what this video is for. First thing is, we got to add some context. What's a linker? So, in my last two videos, we were talking about this drug called the PROTAC, right? Anchor, linker, warhead. It's a square, line, and triangle. This is a rudimentary model of a PROTAC, right? So a PROTAC's job is to join this E3 ligase, which is right here, and this protein of interest, which is right here. This E3 ligase carries a signaling protein called ubiquitin. It's a 76 long amino acid protein that signals the proteasomes, hey, I want this protein destroyed, right? And the goal of a PROTAC is to bring these two proteins close enough to where ubiquitin can transfer to the protein of interest, essentially destroying it. Now, why linker design is so important, and which is one of the reasons I'm so interested in linkers, is this idea of the selection process. So let's understand a little bit about what it means to select an anchor and a warhead. So usually when scientists are designing PROTACs, they have a very specific E3 ligase in mind that they want their anchor to bind to, right? And they also have, obviously, they have a very specific protein that they want destroyed. So in a sense, the anchor and warhead are mostly pre-selected parts of the PROTAC, which means what's the only other variable involved? The linker. How these two are linked together is completely variable. It's changing. It's a difficult problem to it provides a difficult question to answer. It provides a lot of things, and I think that's why linkers are so interesting. It really shows it's the more complicated aspect of a very complicated problem. Now let's get into some of the characteristics scientists look at when they're talking about linkers. And let's get into the types of linkers. Now, let's get into the types of linkers. In terms of broad classifications, scientists use two categories for distinguishing between linkers, and that's flexible linkers and rigid linkers. Now, this is just a list of the flexible linkers and rigid linkers I found from a paper, which then that's pretty much just these are the linkers we're going to go over in the next few videos. So let's get into it. This is a PEG linker, alkyl linker, triazole linker, photocase linker, photolinked linker, cycloalkane-based linkers, fused heterocycle linkers, and aromatic linkers. Now, what are all these functional groups? We're going to figure out in the next video together. But let's talk a little bit about what these mean. Now, flexible linkers mean that the linker can rotate. There's a lot of rotation involved in the linkers. Think sp3 carbons. Think things like that. Like alkyl linker is literally just a carbon chain. PEG linker is literally polyethylene glycol linkers. So it's pretty much just imagine straight carbon chain, but throwing some ethers here and there. Like think large degrees of rotation, and on top of that, think malleability. That's the key idea for flexible linkers. Think malleability. Think I can extend this. I can make it shorter or longer based on my needs. Think ease of synthesis. They're easy to synthesize. These are what happens with the flexible linkers. And in case you were curious, a majority of the linkers right now that scientists have access to are flexible linkers. Why? Because they're easy to synthesize, they're malleable, you can control the length at your discretion, but there's a caveat to that. There's metabolic disadvantages, there's disadvantages with permeability, there's a lot of disadvantages that flexible linkers come with, which is why initially there was a large amount of flexible linkers, but there has always, since the inception of the field, been a push to develop rigid linkers. Rigid linkers, they have metabolic advantages. They have the advantage that hey, if we do this over and over again, we're guaranteed to get the same linkage site. We're guaranteed to do this the exact same way because they're rigid. There's not a lot of rotation. But there's disadvantages to rigid linkers as well. One of them is they're far more specific than flexible linkers. They don't have this degree of rotation. It's harder to extend rigid linkers, which is why the research is a little bit slower into rigid linkers, because they're just harder to synthesize, they're less malleable, things like that. Now, next section, we're going to get into linker characteristics. What do scientists look for in linkers? All right, now to get into linker characteristics. These are what scientists look at when they analyze linkers. These are also things they look at when they classify them. So these characteristics are group type. What's the functional group that's involved? Length. Now, I have a little bit of an interesting way of thinking about length, and I do need to do further research to corroborate how I think about length. But let me explain to you my working idea of what length means. And I know length can seem like a very simple idea at first, but to me it felt a little complicated. So I'll give an analogy as to how I think about linker length. So linker length, think steric interactions, right? Think steric hindrances, things like that, because that's ultimately what you're trying to achieve with length. You're trying to achieve a certain distance between linkers. So imagine you have a friend who's holding a rope, and he's holding that rope to a friend on an elevated surface, okay? Now, there's two lengths we can think about when we think about linkers. Imagine this rope is the linker. We could think about how long the rope is. How long is the rope? That's intuitively what we think about length. But then there's this second idea, which is how far does that rope, how far is the distance between the two friends because of this rope? That's how I think about linker length. Because it doesn't necessarily matter how far the proteins are, how long the linker is, because ultimately you're trying to achieve a certain distance between your protein of interest and your E3 ligase. Because there's always going to be protein-protein surface interaction for this idea of complementary surfaces, which we talked about last video. But that's just a little idea I'm getting out there about linker length. Now, flexibility, rigidity. We talked about this like just now. I don't want to waste your time. I don't want to waste my time. Linking sites. We're gonna get a little bit more in depth into this, but think, where on the warhead does this linker bind to? Where on the anchor does this linker bind to? And we'll talk about why this is important in a sec. So those are linker characteristics. Let's get more in depth on this linking site. Now it's time to get into linking sites. So I'm segmenting this because I think it's a little bit of an important idea to get across why linking sites are so important. So let's look at this, right? Imagine each star is a different site that you can attach your linker to on your anchor or your warhead. So you can draw a line like this, like this, like this, like this, anywhere, right? Now, why this is so important is because the linking site determines the shape of the PROTAC, right? It determines, in determining the shape of the PROTAC, you essentially are directly impacting the shape of the ternary complex. Now, if there's anything that you should take away from my last few videos, it's that proteins have shapes, and their shapes are intrinsic to their function. Meaning, if a protein doesn't have a certain shape, it will not work the way it's intended, right? That's what inhibitors do. That's their whole thing. They just go in, they interrupt the shape, and it's inhibited, right? So why that's so important is the ternary. One of the things that makes PROTACs so great is that they're so selective, because this ternary complex could only form in certain conditions, and one of those conditions, it is in most definitely shape. So in affecting the linking site, you are affecting the shape and thus the formation of the ternary complex. And if the ternary complex can't form, your ubiquitin can't transfer, and the PROTAC doesn't work as it should, which obviously no one wants. So that's why linking site is such an important characteristic that scientists consider. Now we're going to get on to group types. Now let's get into group types. So for the characteristics that I thought were most important to include in this video, for group type, there were three that I thought were super interesting and important. So one of them is molecular weight. How heavy is the group, right? How heavy is the linker? How heavy are the functional groups involved in the linker? How heavy do these functional groups make the linker, right? Then we have HBA and HBD sites. Now, HBA sites are called hydrogen bond accepting sites, and HBD sites are hydrogen bond donating sites. And for the case of PROTACs, I'm not exactly sure in other cases if it means anything different. But what I can say is for PROTACs, these are treated pretty similarly, HBA and HBD sites. Why is that? Because hydrogen bond donating sites and hydrogen bond accepting sites essentially do the same thing. And what is that? They form hydrogen bonds. They allow the formation of hydrogen bonds. And can any of you guess what's a molecule that forms hydrogen bonds that's readily available in the body? If you said water, you are right. What these sites are is these are sites for water to join onto the molecule. And let's explain why it's a little bit bad. But first, let's explain Lipinski's rule of 5, right? Lipinski's rule of 5 outlines specific guidelines for if a molecule is unaided by transporter protein, it has to reach these specific requirements, or else there's a sharp drop-off in permeability, right? I believe the number specifically was less than 500 Daltons, 10 HBD sites, less than 10 HBD sites, and less than 5 HBA sites. Now, there is a little bit of discord into Lipinski's rule of 5 in the sense that there is the idea that most drugs are in fact aided by a transporter protein. So then the logic kind of becomes, well, what's the point of the rule if everything's an exception? I mean, chemistry, like everything's an exception, but we still have rules for stuff. But that's besides the point. So, but I would like to explain, I think Lipinski's rule is very important. And I think it is because maybe his numbers, they were right, first of all, which is crazy, because from what I've read, Lipinski had very little resources compared to what we have now. So Lipinski's numbers were not only right, but the logic he outlined is it still governs the ideas of permeability. Why is that? Well, because how I think of transporter proteins, imagine you're helping your mom take in the groceries, right? And she says, oh, okay, you need to take in, let's say, like a medium big object, like an air fryer. Obviously, can't carry multiple things on top of an air fryer, but you can take in the air fryer no problem, by yourself, right? Now let's say she says, oh, you have to take in this desk, right? Big desk. Desks, I don't know if you're crazy strong or something, but hard taking a desk in by yourself. You might need some help. That's what a transporter protein is, right? A transporter protein offsets Lipinski's rule. It doesn't violate it. That is the important thing to keep in mind. Like there's still limits that follow the same logic as Lipinski's rule of 5 that are set even with the aid of a transporter protein. Like let's say you could only have 2 people max, and let's say your mom says, oh, you need to take in this bed. You can't do that. Like bed's heavy, right? So what's important is to understand that Lipinski's logic, it's still very, very clear, especially when you read literature and it says something like Lipinski's rule of 5 there's like an exception to it. No. When they say exception, they always mean it's offset, because you can't violate Lipinski's rule of 5 because it's just very logical. Like the logic is very, very sound. Let me explain why. Lipinski's rule of 5 outline things that make it hard for cells to hard for molecules to go through the cell membrane, right? So let's say molecular weight, right? I have a pointer finger. Molecular weight, right? So molecular weight, if something's too heavy, like let's say something weighs like 1,500 Daltons, even if you have a transporter protein, it's still going to be pretty hard to get across the membrane. Lipinski said specifically 500 Daltons, hey, it's going to be really hard to get across the membrane. But obviously, transporter proteins are involved in most drugs. Now, HBA and HBD sites. Let's talk about why that makes it more difficult to go across the membrane. So an HBA, let's say you have this molecule right here, right? Tons of HBA and HBD sites. where water is formed, right? The phospholipid bilayer is a nonpolar thing, meaning that in order for this molecule to go through the phospholipid bilayer, it has to shed. It's not only nonpolar, but it's also hydrophobic, meaning that it has to shed all these water molecules before it goes through the cell membrane. Okay? Now, why is that important? Because think of this molecule. I think the only way I can explain this is through an analogy, because I'm not crazy comfortable with my understanding of it, but I am comfortable with the analogy. So there you go. So imagine you're sitting on your couch and you're super comfortable. Let's say you have a soda, you have some popcorn next to you, like you're comfortable, right? And let's say you have to get up and go do something. You have to go put your soda away, you have to go put your popcorn away, you have to do all that. Now you're uncomfortable, right? So what the molecule essentially has to do is it has to get rid of these water molecules that have a strong bond, and it has to break that hydrogen bond that it formed at essentially no benefit. And so think of it as like a penalty. So every time it has to break these bonds, it's not getting that much in. It's not get. It costs energy to break that bond, right? And they're not getting a ton of things in return. So what this does is it creates a penalty, and the more and more hydrogen bonds it has to break, the greater and greater this penalty causes. It becomes, and then now if it breaks all these hydrogen bonds as it tries to go through the phospholipid bilayer, well then, where's the energy coming from, right? And that goes to an important point where there's random kinetic energy that happens from molecules moving around. That's not like a set number, that's a range. So it pretty much depends on how much of a kick from this random kinetic energy can this molecule get to go through the cell membrane. And why this is so important is because obviously if you have a molecule that has like a lot of HBA and HBD sites, then it's going to have a really hard, you're pretty much leaving it up to chance as to whether or not it's going to be able to permeate through this, go through the cell membrane efficiently, which then means that there's the larger and larger sample size you get, and obviously with when you ingest like a pill, that's a large sample size in and of itself. There's not, you don't want to affect like one cell, you want to affect like thousands of cells. So once you increase the sample size by taking like by having this drug like affect like 1,000 cells or 1,000,000 cells, right? Then the efficiency, then the trend starts to appear where this drug that has a lot of HBA and HBD sites is less efficient. So if that was a little bit confusing to you, I do apologize. But take away from this that the higher your molecular weight goes, the higher your HBA sites go, the higher your HBD sites go, you will have a less easily a molecule that less easily is permeable through the cell membrane, which is important because that molecule is usually a drug, and you want that drug to go into the cell membrane. Now, that's going to be the end for this video. I think I'm the next video I have in store is going to be a video about triazoles. They're a type of rigid linker, and I just find it very interesting. The video after that, I'm going to be redoing my first and my second video that I ever published to this channel, because I think I really don't like the fact that it was just recorded on Zoom. I thought that was like pretty sloppy, so I'm gonna try get those videos a little better so the information becomes easier to digest. Thank you. See you next time.